Alright, so to start off today, we are finishing our discussion of the convergence of the campbell-hausdorff formula. So I'll write that at this top here, convergence of the campbell-hausdorff formula. Alright, so now if you recall, we had two theorems we were going to prove at the same time, which is essentially relating every Lie algebra back to a Lie group, and a theorem stating that. So I'll just write them down here. Theorem in character k being 0, a finite dimensional Lie algebra G is the algebra of an analytic group chunk. And our second theorem, that the group law we defined on we reconstructed the group chunk, we found what f would have to be, and our second theorem is that f is convergent. So we first note that since a scaling as change of coordinates does not affect convergence, we can scale our basis so that the absolute value of lambda times gamma is at most 1 over n squared. And this is, we're assuming this is on our basis without loss of generality as we can get. And so then this gives us a lemma, which is an equivalent of our old lemma, just under these new conditions, which states that if we have a P and E homogeneous of degree R, then if Z is X or Y, the adjoint of Z on P is homogeneous of degree R plus 1, and the absolute value, the norm of the value of add Z on P is at most the size of P. Now we use Dinkin's formula, which we reviewed, which we did not review. It's from a different book, but just go with me on this one, I guess, to find explicitly f being theta of z bar explicitly. As f of x and y being the sum over nu of f nu of x and y with f nu, the homogeneous part, of f of degree nu as f nu of x and y is 1 over v, and then times adding over the sum of p plus q having to equal v of f prime of p comma q of x comma y plus f double prime sub p q of x comma y, and once again we will need explicit forms of each of these. Start with that. So we have f prime pq of x and y being the sum over p1 plus pm adding to p. We have every way of splitting q1 and qm up into q, where each pi plus qi is at least 1, and each pm and our final pm itself is at least 1. And this is our -1 to the m plus 1. Yeah, I'm sure we saw this before. I recognize this formula. Over m times the adjoint of x to the p1 times the adjoint of y to the q1 all the way up to the adjoint of x to the pm acting on y, and this is scaled down by p1 factorial, q1 factorial, all the way up through pm factorial. And we're going to have another formula vaguely similar for our second, or double apostrophe. The sum of p1 through pm minus 1 being p minus 1, and q1 plus through qm minus 1 adding up to give q, and each pi and qi adding up to be at least 1 of our -1 to the m plus 1 over m times the adjoint of x to the p1, adjoint of y to the q1, keep alternating all the way up to adjoint of y to the q sub m minus 1, acting on x, scaling by p1 factorial, q1 factorial, all the way through q sub m minus 1 factorial. With, by our previous lemma, each numerator being a homogeneous polynomial of degree nu with whose coefficients having absolute value less than or equal to 1. Also, with the expression for square brackets, we see by induction that the number of monomials in each numerator is less than or equal to n to the 2 nu. Hence, we can majorize each numerator by a real polynomial degree v in x and y, which is the sum of n to the two new monomials, each with a coefficient of 1. Such a polynomial is estimated at a radius vector s through s in R to 2n by n to the 2 nu times s to the nu, which is equivalently equal to n squared times s to the power of p plus q. By a previous lemma, the third lemma I think from yesterday, in this section at least, the integers in the denominator can be estimated by the absolute value of nu being at most a to the nu, which is a to the p plus q. Likewise, the absolute value of m is at most a to the m, which is at least a to the p plus q. And also our collection of p1 factorial, q1 factorial through p m factorial, and our p1 factorial, q1 factorial through q to the m minus 1 factorial, both of which are at least a to the sum of the pi and the sum of the qi, which is a to the p plus q. Hence, for t being equal to n squared s over a cubed, the components of the formal group law f can be majorized by twice the formal sum we saw in our third lemma, by twice the formal sum from our third lemma we saw last time, since that we saw that converges for small t f converges for small s. Okay, and thus we get everything that we want. Now, we have a couple remarks to follow this up. When G is nilpotent as the algebra f is a polynomial and converges trivially. Secondly, to estimate our radius of convergence, we can estimate the constraints in the proof. Let's see. You can see that the series in our previous lemma 3, namely converges for t less than square root of 2 minus 1 over square root of 2. So f converges on every, say, polydisk of radius r in all dimensions. So I'll call it a disk of radius r, where r is less than a cubed over n squared times square root of 2 minus 1 over square root of 2. This estimate, it says here, this estimate is bad, but no good estimates are known when k is real or complex. Now, suppose k is ultrametric and the restriction of the absolute value to the integers is p-adic. Further, we suppose G is a Lie subalgebra of the algebra of our generalized general linear group on R, where R is a finite dimensional associative algebra with unit over K. That is, G is a subset of R, and our bracket is the standard on G. And we're also going to assume, just to make things easy, that multiplication satisfies absolute value of x times y, being at most the absolute value of x and the absolute value of y. We can then e to the x in the way that I'm sure you know, x to the n over n factorial, which defines an isomorphism of an open additive subgroup M onto itself. So it's an automorphism. Don't know why they seem to not like using that word in this book. where M is the set of X in our R, where with a valuation less than the valuation of P over P minus 1. We may define a group law on M by gxy to equal z as there exists a unique z in M such that e to the x times e to the y is equal to e to the z. Which agrees with the Campbell-hausdorff formula when it converges. When the latter, you know what I'm saying, when the latter converges. And Lazard has shown it converges on M. By restriction, we can obtain convergence of the Campbell-hausdorff formula on M intersecting G. And one last remark, since we know when K is ultrametric, every analytic group chunk corresponds to an analytic group, which is a Lie group. Then we have every Lie algebra is the algebra of a Lie group over K. Alright, and that is, yeah, it's been like 20 minutes, yeah. It's a bit over 20 minutes, so we're going to start our talk now on point distributions, which I think is mainly just an analytic tool we're going to be using coming up. Point distributions. I should check, are we going to be able to finish this? Maybe. So, point distribution is a distribution whose support is concentrated at a single point, as you might have gotten from this. And going forward, we will assume K is a commutative ring with unit or a rational algebra. in a informal questions and in a setting of convergence questions, it can be a field complete with respect to a non-trivial absolute value in convergence questions. So, first off, I'm going to let X be a manifold and pick some P in X. Recall we have a local ring which we wrote as H underscore P of X at P with a maximal ideal M sub P, with Fn has a P dimension, Fn is the P dimension of X, then our local ring is isomorphic to the ring of convergent power series in n variables. We'll give H underscore P the topology defined by letting the powers of MP be a basis for the neighborhoods of 0. With K, the subspace topology on our base K in HP being given the discrete topology. We now define a point distribution on H sub P to be a linear form U from H bar from P underscore P to K such that it first off has to vanish on some power of M sub P, and secondly U is continuous on H underline P with respect to the discrete topology on K. And we may extend, of course, we may extend u to be a linear form on the completion h hat underscore p which is isomorphic to the formal power series in n variables on K. Alright, secondly, we are going to we're going to let K be a commutative ring with unit, and let H be the formal power series ring in n variables over K. Let M be the ideal generated by x1 through xn, and for positive integer r, let's write it like this. We're going to let h sub r be our h over m to the r plus 1. Also, we're going to let u sub r be the dual of h sub r, which is the linear maps, of course, from hr to k. Then, as above, the linear form u on h is a point distribution f what? Is it this one? Okay. Sorry, I hit something I didn't know what it did. If the following equivalent are satisfied. Oh, and these are equivalent as well. I skipped over that last time. Okay, well, first off, we have u vanishes on a power of m sub p. Secondly, u is continuous on h underline sub p with respect to the discrete topology on K. No, that's the old. So I'm sorry. I'm so tired. That's just rolled conditions again. So for this one we have r being an integer such that u vanishes on m to the r plus 1. Which means it factors through the projection of h onto hr. And secondly, we have u is continuous on h. We're going to define capital U to be a subspace of H star can be the subspace of point distributions. Now consider the projection from H onto HR. Dualizing, we get an injection from U sub R to H star. So U may be identified with the union of the images of the U sub R. Now we're going to look more closely at the K-module structure of H and U. So, by definition, H is the product over alpha of K times X to the alpha. For an alpha, we may define an element delta to the alpha in U as delta alpha of X beta being just checking whether or not alpha and beta match up. 1 if they do, 0 if they don't. Then delta alpha of U are clearly linearly independent on K over K. And since H, U, and U vanishes on a power of M, some power of M, we may write each U as a finite linear combination over K elements of the form delta to the alpha. Let's get 2 lemmas for free. Well, 1 lemma for free, seeing that U is the direct sum over alpha of K times Km of delta to the alpha. And we also get that U star is just H. Proof, we know that U is inside H star. We have a map. There's the canonical injection of H into H double star, just being evaluating functions at that point, which then has an image in U star. Under this map, X alpha is identified with the linear form on U as being 1 on delta to the alpha and 0 on delta to beta, where of course beta is not alpha. Then U star being L times the direct sum over alpha of K times delta to the alpha. K can be also written, we can pull out that sum as a product of the linear maps from each K times delta to the alpha onto K, which is just the product over alpha of K times X to the alpha by this identification, which as we know is just H. And we note that epsilon being delta 0 is the Dirac delta distribution. Now, we consider the multiplication as consider the structure multiplication, which rate as move from H tensor H into H induces on U. In H times H, consider the ideal M hat, which we can write, which is M tensor H plus H tensor M. We give H tensor H the topology defined by powers of M hat. Then mu, of course, is continuous, and so extends to the completion H hat tensor H of H tensor H. We're going to let U underscore be the space of point distributions of H tensor H, or equivalently H hat tensor H. Then the dual map mu star from H star to H hat tensor H star induces by restriction a diagonal map, which we're going to write as delta from U to this U underline. And this terminology is justified by a lemma which states that, first off, the canonical map from U tensor U to U underline is an isomorphism, and secondly, this is called Leibniz's formula here, where delta of capital delta alpha is the sum over beta plus gamma equaling alpha of delta beta tensor delta gamma. Let's look at the proof of this. And we're almost done. So we're going to let yi be xi tensor 1 and zi be 1 tensor xi. Then the canonical inclusion h tensor h to k of y1 through yn and z1 through zn, which we write as h underline extends to an isomorphism of the completion of h tensor h and h underline. Under this identification, U underline has a canonical basis delta of alpha beta by delta of alpha beta of y to the alpha of y alpha z beta no, actually these are going to be y to the regular old a and z to the b, and of course we need alpha to match up with a and we need beta to match up with b. Then the map from U tensor U to U underline identifies the basis element delta alpha tensor delta beta with the basis element delta of alpha comma beta. These are the basis elements of U tensor U and U underline, so that's part 1. And for part 2, we now want to consider the operation delta of delta alpha on a typical monomial y to the beta z to the gamma. Well, then delta of delta the alpha on y beta z gamma is delta to the alpha of mu of y beta z to the gamma, which is delta to the alpha on delta the alpha on x to the beta plus gamma, which is just going to check if alpha is equal to beta plus gamma. which, if you work that out, all for every possibility, that just gives us our second formula up above. We have one more remark, and then we can call it for an episode, where we note that since H is just k tend to k, direct sum of k and m, we can generalize the tangent notion of the tangent vector to this algebraic situation. We say u in u is a tangent vector if, and we note these conditions are equivalent. First off, u from h to k is a derivation. Maybe that's the restriction of u? No. I don't know. Don't worry about it. Lost my train of thought there. Secondly, u vanishes on k and on m squared. And thirdly, u is primitive for delta, which we recall means delta of u is u tensor 1 plus 1 tensor u. And we've seen that these are all equivalent before, so we're actually going to call it there for an episode. And yeah, thank you for watching. I'm tired.